Hold still for a moment and consider the atoms in your body. They are in your hands, behind your eyes, resting in this bed with you. You have always been told that matter simply exists, that it was here first, the solid ground beneath everything else. But the physics says every one of those atoms should have been destroyed in the first second of time, for every 1,000,000 particles of antimatter. Made just after the Big Bang, there were only 1,000,000 particles of matter. That is the story of your existence, written as a rounding error. One extra particle in a billion, everything else cancelled out. The stars, the planets, the oceans, the body you're resting in right now, all of it is built from that thin remainder. You're not made of what the universe began with. You're made of what barely survived it. If a quiet idea like that is why you came here, consider following along and leaving a like, and know that these scripts live on Spotify too. That is all the asking there will be. Now the rest belongs to the physics. To see what nearly erased you, we have to go back. Not to the beginning of the Earth, to the beginning of everything, to the first fraction of the first second, when there was no space to speak of and no cold anywhere at all. In that first slice of time, the universe was not made of atoms. It was too hot for atoms. It was too hot for the pieces inside atoms to even hold together. The temperature was somewhere around 7.2 trillion degrees Fahrenheit. Nothing you have ever seen comes close to that number. The core of the sun is a cold, dark cellar beside it. At that heat, matter had no shape at all. There were no protons, no neutrons, none of the familiar bricks. Instead, there was a plasma of quarks and gluons, the raw ingredients themselves, moving free and unbound. Physicists call this stretch the quark epoch. It ran from about a trillionth of a second to about a millionth of a second after the Big Bang. A window so brief you cannot feel it, and yet everything that would ever matter was decided inside it. Try to picture that plasma. It is denser than the heart of any star that burns in the sky today. It does not glow with a light you could ever look at. It radiates so fiercely that a single quark cannot cling to the quark beside it. There is no chemistry here. There is nothing solid. There is only heat and pressure, and a formless soup with no bottom, filling every scrap of space there is. Then the universe did the one thing it has never once stopped doing. It expanded, and as it expanded it cooled. Cooling sounds gentle. This was not gentle. As the temperature fell below roughly 20 trillion Kelvin, the free quarks finally slowed enough to catch hold of one another. They locked together in threes, and in locking together they froze into the first real particles, protons, neutrons, the bricks of every atom that would ever be built. But the quarks did not only build matter. For every proton they made its exact mirror image, an antiproton. For every neutron, an antineutron. This is the part that should stop you where you lie. The early universe did not prefer matter. It made matter and antimatter together, in the same breath, in what should have been exactly equal numbers. Antimatter is not a fantasy. It is real, and it is simple to describe. Take any particle you know and flip its electric charge. A proton carries a positive charge. Its antiparticle carries a negative one. Everything else about the two is a perfect match. The same mass, the same stubborn solidity. They are twins, born facing opposite directions, and twins like these cannot share a room. When a particle of matter meets its antimatter partner, they do not bounce apart. They do not shatter into smaller pieces. They vanish. Both of them convert entirely into light, into a flash of gamma radiation, their whole mass spent in a single instant. Nothing physical is left where they had been, only energy streaming outward. Now hold the whole scene in your mind. A universe filled edge to edge with matter and antimatter in nearly equal numbers, all of it packed tighter than anything has been packed since. Every particle has a twin somewhere in that crush, and as the plasma cools, twin after twin finds its partner and annihilates. Not once, not 1,000 times, trillions upon trillions of times every second, everywhere in the universe at once. This is the near total erasure the title points to. It was not a war. There was no side that fought harder or wanted it more. It was a silent, symmetric cancellation, matter and antimatter deleting one another in matched pairs across the whole of space, spending themselves into a flood of gamma light. In well under a second, almost the entire contents of the young universe unmade itself. Feel how thorough that was meant to be. If the numbers had been exactly equal, the story would end right there. Every particle would have found its twin. Every pair would have vanished into light. There would be no leftover matter to cool into gas, no gas to collapse into stars, no stars to forge the carbon and the oxygen and the iron that are threaded through your bones and your blood tonight. The universe would be a smooth sea of radiation drifting through an empty dark, with nothing solid anywhere in it, and no one to notice the emptiness. That is what the standard model of physics, our best and most tested rulebook for how particles behave, actually predicts. Equal parts, total cancellation, a cosmos of pure light and nothing else at all, and yet, here you are, with weight and with warmth, lying in a bed made of atoms, in a room made of atoms, under a sky full of stars made of atoms. Every one of those atoms is a survivor of that first second, which means the numbers were not exactly equal after all. Somewhere in the counting, matter held the thinnest possible lead, about one extra particle for every billion matched pairs. That is the entire margin, 1 in a billion. When the annihilation had finished and the storm of light settled, the billion matched pairs were gone, spent completely into radiation. Only the lonely extras remained, the 1 in a billion particles that had no partner left to cancel them. Those unpaired survivors are everything. They are the whole of the material universe. They are the stars and the planets. They are you. We are not merely guessing at any of this. The universe left behind a receipt. Each time a pair of particles annihilated, it released photons, particles of light. Those photons did not simply disappear. They are still here, spread through all of space, stretched and cooled by nearly 14 billion years of expansion into a faint even hum of radiation that fills the sky in every direction you could point. We call it the cosmic microwave background. It is the oldest light there is, and it has been travelling since before the first star. When physicists count that light, the arithmetic is staggering. For every single proton that survived, there are roughly 1 billion of those photons, 1 billion faint markers of light for every one thing left standing. That ratio, 1 billion to 1, is the fossil of the slaughter. It is the measurable echo of the moment when nearly everything that existed turned into radiation and left only a trace behind. Sit with that ratio a little longer. It means the universe you live in is overwhelmingly made of the ash of an annihilation. The matter, the part you are built from, is the faint residue. The light is the tombstone. You're lying, in a sense, in a graveyard so complete that the graves outnumber the living 1 billion to 1, and you have always simply called it home. There is a way to feel the size of what was lost. Imagine a sand castle as tall as a mountain, grain upon grain packed into towers and walls that run to the horizon. Now imagine almost every grain finding its exact opposite, and both flashing silently away into nothing. When the flashing finally stops, you sweep a hand through what remains, and it comes up holding a single grain of sand. That one grain is the entire visible universe. Everything you have ever touched, or loved, or been, is built from that lone survivor. This is the part worth saying as plainly as it can be said. Every atom in your body, in this bed, in this room, is not what the universe was built from. It is what the universe forgot to destroy. You are the exception the physics did not intend to leave. You are the error that the great cancellation happened to miss. And here is the thought that should keep turning over as you lie there in the dark. Physicists do not know why the exception exists. That is not a soft or modest admission. It is a hard, open wound in modern science. The known laws, tested inside the most precise machines human beings have ever built, do allow for a tiny lean toward matter over antimatter. But when they measure that lean, it comes out far too small. It is many orders of magnitude weaker than what would be needed to leave behind the amount of matter we actually find. The rulebook permits a faint whisper of imbalance. The universe needed a shout. So the survivor is real, and the survivor is you, and the reason the survivor survived is missing from the book. That one extra particle in a billion has never been explained by any experiment anywhere on Earth. It sits there, at the very root of your being here, as one of the deepest unsolved problems in all of physics, the place where the science of the smallest things meets the shape of the entire cosmos and comes up short. You can lie here and follow the logic all the way down, and it keeps holding at every step. If the imbalance had been even slightly smaller, there would be less matter and fewer stars and a thinner, colder universe. If it had been exactly zero, there would be nothing at all. No chemistry, no planets, no slow accident of biology that ends with a mind lying awake, wondering about any of it in the quiet. The margin that made you was almost nothing, and almost nothing turned out to be exactly enough. For a long stretch of human history, none of this could even be asked. Before anyone could wonder why matter had won by a hair, they had to be certain the loser was ever in the room to begin with. Antimatter had to be proven real, not as a strange shadow inside an equation, but as a genuine thing, something you could photograph and hold up against the light. That proof did not come easily, and when it finally came, it came almost by accident. But before anyone could ask why the survivor survived, someone first had to prove its vanished twin was ever real. But before anyone could ask why the survivor survived, someone first had to prove its vanished twin was ever real. That proof did not begin in a laboratory. It began on a chalkboard, inside an equation, in the mind of a very quiet man. His name was Paul Dirac. The year was 1928. He was a British physicist with a reputation for saying almost nothing at all, and he had set himself a problem that most of his peers thought was decades away from any answer. He wanted to describe the electron correctly, not roughly, exactly. By 1928, physics had two towering theories, and they did not speak to each other. One was quantum mechanics, the rulebook for the very small. The other was Einstein's special relativity, the rulebook for anything moving near the speed of light. Electrons are very small. Electrons also move very fast, so an electron lives in both rulebooks at once, and nobody had written a single equation that honoured both. Dirac did. He built a formula that folded quantum mechanics and special relativity together into one clean statement about how an electron behaves. It worked. It predicted the electron's magnetism. It predicted its spin. It matched experiment with a precision that felt almost unfair. But the equation had a second answer. Here is the strange part. A good physics equation often has more than one solution, the way the square root of a number can be positive or negative. Dirac's equation described the ordinary electron beautifully. Then it turned around and described something else. A particle with exactly the same mass as the electron, the same weight to the last decimal, but the opposite electric charge. The electron carries a negative charge. This other thing carried a positive one. At first, nobody wanted it. An unwanted answer is an embarrassment. You look for a mistake. Dirac looked. There was no mistake. The second solution sat there in the mathematics, patient and undeniable, describing a mirror image electron that no one had ever seen. For a while he tried to explain it away. Maybe the positive particle was just the proton, he thought, the heavy particle already sitting in every atom's core. But the proton weighs about 1,836 times as much as an electron. The equation demanded an exact twin, identical in mass. The proton could not be it. So in 1931, Dirac did the boldest thing a theorist can do. He stopped apologizing for the equation. He committed to it. He said in effect that if the mathematics insist this particle exists, then it exists, and we simply have not found it yet. He predicted a new kind of matter, a mirror electron, what we now call antimatter. Sit with how strange that is for a moment. A man had predicted an entire hidden half of reality using nothing but a piece of chalk and a refusal to look away from his own arithmetic. There was no photograph. There was no track in a detector. There was only an equation that would not stop being true. Before we go further into how that prediction was proven, a small ask. If this quiet corner of the universe is the kind of place you like to end your day, a like or a subscribe helps more people find it, and these scripts live on Spotify too. That is all. Now settle back in. Because the equation was only half of the story. Somewhere on the other side of the world the second half was already coming, and the man carrying it had no idea Dirac's prediction even existed. His name was Carl Anderson. He was a young physicist at Caltech in Pasadena, California. He was not hunting for antimatter, he was studying cosmic rays. Cosmic rays are particles that pour down onto the Earth from deep space. They rain through the roof, through the walls, through you, every second of every day. Anderson wanted to photograph them. To do that, he used one of the most beautiful instruments physics has ever built, a cloud chamber. Picture a sealed box small enough to sit on a table, roughly the size of a dinner plate. Inside it, the air is filled with a vapor pushed to the very edge of becoming liquid. Supersaturated, physicists call it. The air is so loaded with moisture that the smallest disturbance makes it condense. Now a charged particle streaks through. It knocks electrons loose along its path, and the vapor condenses on that trail exactly the way your breath fogs a cold window. What you get is a thin white contrail hanging in the box, an invisible particle, smaller than an atom, leaving a visible line you can photograph. It looks like the vapor trail of a jet crossing a clear sky, except the jet is tinier than anything you will ever see, and the sky is a fogged glass box in a California basement. Anderson added one more thing, a powerful magnet wrapped around the chamber. This is the clever part. A magnetic field bends the path of a moving charged particle, and which way it bends tells you the sign of its charge. A negative particle curves one way. A positive particle curves the other. The tighter the curve, the lower the particle's momentum. So a single curved white line in that box is not just a picture. It is a full confession. It tells you the particle's charge, its energy, its direction, all at once. On the 2nd of August 1932, Anderson developed one of his photographic plates and found a track that did not make sense. The curve was clean. The tightness of it, the way it bent, matched an electron almost perfectly. Same mass, same behaviour. But it was bending the wrong way. An electron, in that field, should have curved to one side. This track curved to the other. Charge and mass of an electron, but the opposite sign. A positive electron. Anderson checked everything. Was it an electron travelling the other direction? He had thought of that. He had placed a lead plate across the middle of the chamber for exactly this reason. A particle loses energy passing through lead, so its curve tightens on the far side. That told him which way the particle was moving, and moving that way, with that curve, in that field, it could only be one thing, a particle as light as an electron carrying a positive charge. Here is the coincidence that makes this story almost too neat to believe. By most accounts, Anderson did not know about Dirac's prediction when he found it. He was not looking for the mirror electron. He was reading cosmic ray tracks one photograph at a time. The theorist had reasoned this particle into existence from pure mathematics in England. The experimentalist had stumbled onto its footprint in a fogged box in California. Two men, an ocean apart, arriving at the same hidden truth from opposite directions almost independently. That almost never happens in physics. Usually theory chases experiment, or experiment chases theory. Here they simply met in the middle, in the same handful of years, and shook hands over a particle neither the world had ever seen. Think about what Anderson was actually holding. A single curved white line on a piece of black film, nothing more. But if that line was real, and it was, then the universe had a mirror half. Every particle of matter might have a twin made of the opposite charge. The equation had said so. Now the photograph agreed. The claim was enormous, so it needed confirmation, and it got it fast. In 1933, at the Cavendish Laboratory in Cambridge, two physicists named Patrick Blackett and Giuseppe Occhialini went further. They built a cleverer cloud chamber, one triggered by the cosmic rays themselves, so it only took a picture when a particle was actually passing through. They caught these positive electrons by the dozen. They saw them born in pairs alongside ordinary electrons, and they connected the tracks directly to Dirac's equation, closing the loop between the chalkboard and the film. The new particle needed a name. It was the positive twin of the electron, so they called it the positron, a positive electron, the first piece of antimatter humanity had ever identified. The honours came quickly, and they were young men's honours. Carl Anderson won the Nobel Prize in Physics in 1936, just 4 years after that photograph. He was 31 years old. That makes him one of the youngest people ever to win the physics prize. A man barely out of his 20s handed the highest honour in his field for noticing that a line curved the wrong way. And once the door was open, the mirror world kept revealing itself. If the electron had a twin, so should everything else. Physicists went looking, and they found. The antiproton, the mirror of the proton, was created and confirmed in 1955. The antineutron followed in 1956. Every particle of ordinary matter, it turned out, has an antimatter counterpart waiting in the mathematics and, given enough energy, in the laboratory. Decades later, physicists would even build whole atoms of antimatter, antihydrogen, the mirror image of the simplest element there is. But hold on to the moment it all started from, because it is easy to imagine that a discovery this large came from a grand hunt, a team, a plan, a mission to find the mirror world. It did not. Antimatter was not found by looking for it. It was found because a young man in Pasadena developed a photograph, saw one faint white curve leaning the wrong way, and trusted what the curve told him. That single wrong curve, on a single strip of film, rewrote what matter is. It confirmed that reality comes in two halves. And it turned Dirac's lonely equation, the one with the answer nobody wanted, into one of the great predictions in the history of science. You can feel the quiet symmetry of it as you lie there. A man who barely spoke, reasoning a hidden particle into being from an equation. A man who was looking at something else entirely, catching that same particle by accident in a box of fog. Neither one saw the whole picture. Together they saw all of it. And it raised a question that still hangs over everything. If matter has a perfect mirror twin, identical in every way but charge, then the universe should have made them in equal amounts, the same weight, the same number, perfectly balanced, a cosmos split exactly down the middle. The positron proved the mirror was real. It did not yet prove the mirror was flawed. To everyone in the 1930s, antimatter looked like an immaculate reflection, matter's exact and opposite equal, differing only in sign. That assumption felt safe. It felt obvious. It felt like the kind of clean symmetry the universe ought to keep. It was also wrong, though no one would learn that for another 30 years. The positron answered one question, and quietly asked a far larger one. A single mirror particle for the electron could still have been a fluke. The electron is the lightest of the everyday particles, feather-light and easy to bend in a magnet, and maybe its twin was a special case, a private oddity of the smallest thing inside the atom. What no one yet knew was whether the mirror ran all the way down, whether the proton, the heavy anchor sitting in the centre of every atom in your body, also kept a hidden double. There was a reason to suspect it might. The whole idea had come from an equation. Back in 1928, the mathematics that described the electron had refused to give just one answer. It insisted on a second solution, a particle of the same mass with the opposite charge. If a piece of pure algebra could conjure a mirror out of the electron, perhaps the mirror was a rule of nature rather than a single lucky exception. But an equation is not a photograph. Someone still had to catch the proton's twin in the world. That was the harder catch. A proton weighs nearly 2,000 times what an electron weighs. To make its antimatter double, You cannot simply wait for the right cosmic ray to drift through a fogged box. You have to build the energy yourself, concentrate it, and pour it into a machine large enough to hold it. In 1955, that machine existed. It was called the Bevatron, an accelerator built to drive protons together at enormous speed. When physicists ran those collisions hard enough, something new appeared in the wreckage. A particle with exactly the mass of a proton, but carrying the opposite electric charge. Where the proton is positive, this one was negative. In every other respect, it was the same. The antiproton was real. Picture a mold. You press a shape into it, and every casting that comes out is identical, ridge for ridge, curve for curve. The antiproton is a casting from the proton's mold, flawless in every dimension, with a single sign quietly flipped. Same weight, same size, same fierce grip on the particles around it. Only the charge reversed, as though the mold had been read in a looking glass. You could confirm it by the way it died. When an antiproton meets an ordinary proton, the two do not bounce apart. They cancel. Their combined mass, roughly 1,877 million electron volts of it, converts into a burst of energy and lighter fragments in an instant. That clean vanishing into light was part of how physicists knew exactly what they had built. But the proton is only half of the nucleus. The other half is the neutron, and the neutron posed a stranger puzzle. It carries no electric charge at all. If antimatter were simply matter with its charge flipped, then a neutral particle would seem to be its own twin. Nothing to reverse, nothing to distinguish. A mirror with no reflection to give back. The following year, in 1956, physicists found the antineutron anyway. It exists, and it is genuinely distinct from the ordinary neutron, even though the two share the same neutral face. The mirror, it turned out, did not hang on charge alone. Something deeper inside the particle had been reversed, some inner ledger that stays hidden until an antineutron meets a neutron, and the two annihilate. With that, the entire core of ordinary matter had been mirrored. Proton, neutron, electron, the three pieces every atom is built from, each now had its confirmed opposite. Once you have the parts, the next step is almost impossible to resist. If a proton and an electron can bind into an atom of hydrogen, the simplest atom in the universe, then an antiproton and a positron should bind into an atom of antihydrogen. The antimatter reflection of the very first element on the periodic table. For decades this stayed a thought experiment, because holding antimatter still long enough to build with it is brutally hard. Anything it touches is ordinary matter, and the lightest contact means instant annihilation. You're trying to store a flame in a box made of kindling. Now physicists do it on purpose, and they do it routinely. At a facility plainly named the Antimatter Factory, they manufacture antihydrogen atoms, suspend them in shaped magnetic fields so they never brush a solid wall, and then study them at leisure. Across recent experimental runs in 2023 and 2024, one team there produced more than 2 million atoms of antihydrogen. Whole atoms of the mirror world, made to order, held in place, and examined in fine detail. Here is what those 7 decades of patient catching added up to. It was never just the electron. It was never just the proton. Every single kind of matter particle that has ever been found has turned out to have an antimatter counterpart waiting behind it. The list is complete. Point at anything the universe is made of, any building block underlying the entire periodic table, and there is a shadow version of it. The same mass, opposite in the ways that count, ready to be written into a second catalogue that mirrors the first one line for line. Think of it as 2 ledgers laid side by side. One holds every kind of matter. The other holds an exact antimatter twin for every entry. No gaps, no missing pages, no lonely particle without its double. Whatever appears on one side has its reflection on the other. The mirror is not partial. It is not a rough approximation. As far as anyone has ever measured, down to the last decimal a machine can reach, it is total. And that completeness is exactly where the trouble begins. You might expect a perfect, unbroken mirror to make the universe easier to understand. It does the opposite. If matter and antimatter are true twins, cast from the same moulds with only a sign reversed, then the young universe had no reason to prefer one over the other. It should have made them in equal amounts. And equal amounts is a death sentence for everything. Every particle would have found its twin, cancelled, and dissolved into light, leaving nothing behind to gather into a star, a planet, or a person lying in the dark. The more flawless the mirror looked, the sharper the question grew. A slightly imperfect mirror you could live with. A crack, a flaw, some quiet place where matter was favoured even faintly would be enough to leave a residue behind after the great cancellation. But everything the confirmation chain revealed pointed the other way. The antiproton matched. The antineutron matched. The antihydrogen atom weighed and measured against ordinary hydrogen matched. Every test said the two halves of creation were identical, so the survival of everything you're made of stopped looking like a natural outcome and started looking like a quiet contradiction of the very symmetry the experiments kept confirming. A perfect mirror should have left an empty universe, a cold sea of radiation and nothing else. Instead, there is you, warm and breathing in the dark, built entirely from the side that somehow stayed. You are the evidence that the books did not balance. For a long time, that was the whole shape of the mystery. A mirror confirmed piece by piece, in accelerators and magnetic traps and photographic plates, until the reflection seemed absolute. Two ledgers that should have zeroed each other out and one of them still full. The neatness of it was almost unbearable because neatness, in this case, is precisely what forbids your existence. If the twin of every particle is a faithful copy, the arithmetic has only one answer, and that answer is nothing at all. Which is why the real turn in this story was not the finding of the mirror, it was the discovery, buried in the fine grain of how these particles decay, that the reflection was not quite as faithful as every mass measurement suggested. Finding antimatter was only the beginning. The deeper shock was that it did not behave like a perfect mirror after all. Finding antimatter was only the beginning. The deeper shock was that it did not behave like a perfect mirror after all. For a while, physicists took comfort in the symmetry. If matter had an opposite, then surely the two were equal and opposite in every way. Swap every particle for its antiparticle, flip the world into its mirror image, and the laws of physics should not notice the difference. That was the assumption. It was clean, it was beautiful, and it was wrong. The break came quietly, the way most of these breaks do. In 1964, two physicists named James Cronin and Val Fitch were working at Brookhaven National Laboratory in Long Island. They were studying a particle called the neutral kaon. You have never seen one, and you never will. It flickers into existence and decays in a sliver of time too short to name in ordinary words. But the kaon had a strange habit. It came in a long-lived version and a short-lived version, and the long-lived one was supposed to obey a rule that everyone believed was absolute. That rule had a name. Physicists called it CP symmetry. The C stands for charge, the P stands for parity, which is just a fancy word for the mirror. Put them together, and CP symmetry says something simple. Take any process, swap matter for antimatter, flip it in a mirror, and it should run exactly the same. The long-lived kaon was forbidden, under that rule, from decaying a certain way. It was supposed to be clean, it was supposed to be honest. It was not. Cronin and Fitch watched, and they counted, and they found that about 1 in 500 of those long-lived kaon decays broke the rule. Not most of them, not half. Roughly 1 in 500. It was a needle buried deep in a haystack of data, a whisper against a wall of silence. But it was real, and it was repeatable, and it would not go away. Think about how small that is for a moment. Out of 500 decays, 499 behaved. 1 did not. That single rebel decay, multiplied across an entire experiment, was enough to prove something enormous. Particles and antiparticles are not perfect mirror images of each other. Nature keeps a preference, a faint, almost invisible lean toward one side. Before we go further, if this quiet corner of the universe is the kind of thing you like to fall asleep to, a like or a subscribe helps more than you would guess, and these journeys are on Spotify too. That is the whole ask. Now settle back and let us keep counting the cracks. The result landed like a small earthquake in the physics world. For decades, symmetry had been the compass. If a law was symmetric, it was probably right. If it broke, something was wrong with your instruments. Cronin and Fitch had shown that the breaking was not a mistake. It was a feature. The universe itself was very slightly biased. 16 years later, in 1980, the two men were given the Nobel Prize in Physics for it. A single decay in 500, and it earned the highest honour their field can give. To feel why it mattered, imagine a coin. Not an ordinary coin, but the coin the early universe was flipping over and over, deciding whether each tiny piece of reality would be matter or antimatter. If the coin were perfectly fair, it would land matter and antimatter in exactly equal numbers. Every particle would find its opposite, every pair would meet and annihilate, and nothing would be left but light. But the coin is not perfectly fair, it is weighted, just barely, toward matter. On any single flip you would never notice. Flip it once, and it looks fair. Flip it 1,000 times, and it still looks fair. You would need to flip it a staggering number of times before the lean showed itself. But the early universe flipped that coin more times than there are grains of sand on every beach on Earth, and then more again. And after enough flips, a bias too small to see on any single toss becomes the difference between an empty cosmos and a full one. It becomes the difference between nothing and you. That is what Cronin and Fitch found. Not the reason you are here exactly, but the first proof that a reason could exist. The first hard evidence that the coin was weighted at all. Before 1964, there was no known way for the universe to prefer matter. After 1964, there was a door, cracked open just wide enough to let a little light through. But a cracked door is not an explanation. Finding that nature cheats is not the same as understanding how the cheating built a universe. For that, someone had to write down the rules of the game. Someone had to say, in plain terms, exactly what conditions the cosmos would need to meet to end up lopsided instead of empty. And in 1967, 3 years after the Kaon result, a Soviet physicist did exactly that. His name was Andrei Sakharov. You may know him better as a dissident, a man who later spent years fighting his own government over human rights. But before that, he was one of the sharpest minds in physics, and he asked a question that few others were asking. What would it take in principle for a universe born balanced to grow up unbalanced? He answered his own question with 3 conditions. All 3 had to be true. Miss any one of them, and you get a cosmos of pure radiation and no observers. The first condition sounds technical, but the idea underneath it is simple. There had to be some process that could change the total count of baryons. A baryon is just the family of heavy particles that includes the proton and the neutron, the building blocks of every atom in your body. If the number of baryons can never change, then whatever balance you start with is the balance you keep forever. To end up with more matter than antimatter, the universe needed a way to actually create a surplus of matter particles from something else. It needed a door through which extra baryons could walk into existence. The second condition is the one Cronin and Fitch had already touched. The universe had to violate both C-symmetry and CP symmetry. In plain terms, matter and antimatter had to genuinely behave differently, not a little differently in appearance, differently in the deep rules that govern how they decay and interact. If matter and antimatter were perfect mirrors, then any process that made a surplus of matter would make an equal surplus of antimatter somewhere else, and the books would balance again. The mirror had to be flawed. There had to be a lean. The kaon had shown that lean was real. The third condition is the strangest and the most beautiful. The universe had to be out of thermal equilibrium while all of this was happening. Equilibrium means everything sitting still, settled, unchanging, running forward and backward at the same rate. If the early universe had been calmly balanced, every reaction that built a little matter would be undone by its reverse, and you would end up right where you started. But the early universe was not calm. It was expanding at a furious pace, cooling by the instant, tearing away from its own past faster than any reaction could keep up. That headlong rush, that refusal to sit still, is what let the imbalance freeze in place before it could be erased. The universe had to be falling forward through time too fast to correct its own mistake. 3 conditions: a way to change baryon number, a flaw in the mirror, and a universe out of balance, changing too quickly to settle. Sakharov laid them out in a short paper that almost no one read at the time. Today they are called the Sakharov conditions, and they are the skeleton on which every serious attempt to explain your existence is hung. They do not tell you the answer, they tell you the shape the answer must take. For a while, that shape seemed within reach. The kaon lean was real. The math had a home. All that remained was to measure the cheating precisely, plug in the numbers, and watch a universe fall out of the equations. So the physicists built bigger machines and hunted for more places where matter and antimatter parted ways. They found them. In the early 2000s, 2 great experiments went looking, one at the Stanford Linear Accelerator Center in California, the other at a laboratory called KEIC in Japan. Instead of kaons, they studied a heavier, stranger particle called the B meson, and they found the same fingerprint. The B meson broke CP symmetry too. Matter and antimatter behaved differently once again, in a whole new family of particles. It was another crack in another mirror, confirming that Cronin and Fitch had not stumbled onto a fluke. The lean was everywhere physicists knew to look, and yet, here is the quiet heartbreak buried in all that success. Every measurement was real, and every measurement was too small. The cheating found in kaons, the cheating found in bemesons, all of it added up to a bias far, far tinier than the one the universe actually needed. When physicists took the CP violation they could measure and asked how much matter it could have saved from annihilation, the answer came back embarrassingly short. Not by a little, by many orders of magnitude. The known cheating could explain a rounding error on a rounding error. It could not explain a single star. That gap has haunted the field ever since. It is quietly one of the biggest unsolved problems in all of particle physics. The mirror is cracked, yes. The coin is weighted, yes. But every crack anyone had ever measured was too faint to leave a universe standing. Something was missing. Some larger source of the imbalance hidden somewhere the instruments had not yet reached. So the hunt continued, patient and stubborn, decade after decade. And it led to a night that finally added a genuinely new chapter, more than 60 years after that first whisper on Long Island. On July 31st, 2025, a team at CERN called the LHCb Collaboration published a result in the journal Nature. For the first time ever, they had caught CP violation not in a meson, but in a baryon. That word matters more than it might sound. Kaons and B mesons are made of 2 quarks, baryons are made of 3, and baryons are the family that includes the proton and the neutron. Baryons are what you are made of. Until that night, every proven case of matter and antimatter behaving differently had lived in the lighter, more exotic mesons. No one had ever confirmed lean in the very particles that build ordinary atoms. Sakharov's first condition asked for a change in baryon number. Here, at last, was a baryon caught bending the mirror. The particle was called the lambda B baryon. LHCb watched enormous numbers of them decay, and they watched the antimatter versions decay too, and they compared. They found a difference of 2.45% between the two. A little under 2.5%, a real and measurable lean between matter and its opposite, and they nailed it down to a confidence of 5.2 sigma. In physics, 5 sigma is the line you must cross before you're allowed to say the word discovery. LHCb crossed it. This was not a hint. This was real. For a moment, sit with what that means across the arc of it all. In 1964, nature was caught cheating in mesons, 1 decay in 500. In 2025, 61 years later, nature was caught cheating in baryons, in the very stuff of you. 2 separate conformations, 2 different families of particles, 2 proofs that the mirror between matter and antimatter is genuinely, permanently flawed. The universe really does prefer matter. It has now been caught in the act twice, and here is the strange, aching punchline that ties both moments together. Both times, the cheating was far too small. The kaon could not build a cosmos. The B meson could not build a cosmos. And even the beautiful new baryon result, that 2.45% difference confirmed at 5.2 sigma, is nowhere near enough to explain the 1 in a billion surplus that let anything survive the first second. Physicists have now caught nature cheating twice, once in mesons and once in baryons, and both times the cheat was too small to explain why you were alive to hear about it. So the picture, after 60 years, is both triumphant and unfinished. The Sakharov conditions can be met. The mirror is flawed, provably, in more than one place. The door Sakharov described is real. But when you walk through it and add up everything measured on the far side, the numbers still do not reach. The known physics accounts for a slice of the imbalance so thin it might as well be 0. The rest is still out there, unexplained, waiting. Look closely at what those experiments actually measured, and a problem appears that has not loosened its grip in 60 years. Begin with the size of the thing you are trying to explain. The leftover was about 1 extra particle of matter for every billion. 1 part in a billion. That thin margin is the entire reason there is anything at all, and physics needs a real physical source for it. You can even read the size of it in the sky today. For every surviving proton in the universe, there are roughly 1 billion photons, the faint fossil light left when almost everything else annihilated. That ratio is the receipt. Something in the first moments had to tip the scale, just barely, toward you. Now count what the laboratories have actually caught. In 1964, at Brookhaven, James Cronin and Val Fitch watched neutral kaons and found them breaking the mirror. About 1 long-lived kaon decay in 500 came out the wrong way. It was real. It earned them the Nobel Prize in 1980. But measured against a whole universe, it was faint. Then came the B mesons. In the early 2000s, detectors at ESLEC in California and at Keck in Japan watched these heavier particles decay, and they too leaned toward matter over antimatter by the smallest amount. Real again. Still faint. Then, on the final day of July in 2025, the LHCb team at CERN announced the newest catch. For the first time anywhere, they saw a baryon break the symmetry, the lambda B, a heavy relative of the proton and the neutron that sits inside ordinary atoms. The difference between it and its antimatter twin was about 2.45%, confirmed at 5.2 sigma, comfortably past the threshold physicists demand before they will use the word discovery. 3 confirmed sightings then. Kaons, B mesons, baryons. And here is the quiet trouble at the centre of all of it. Add every one of those effects together, weigh them as carefully as anyone on Earth knows how. The total still comes out far too small, not slightly short by many orders of magnitude. Imagine a scale that will not balance no matter how much you pile on one side. The cheating we can measure could not have assembled a single galaxy, let alone every galaxy. It cannot begin to account for the atoms in your hands. To feel why that gap is so serious, go back to 1967. A Soviet physicist named Andrei Sakharov wrote down the conditions any universe must meet to end up lopsided toward matter the way ours is. One of those conditions was exactly this, a genuine preference, a real breaking of the mirror between matter and antimatter. Without it, there is no imbalance, and there is no you. So the kaons and the mesons and the baryons settled one thing for certain. Nature does keep such a preference. That part of the puzzle is closed. Nature does cheat. But Sakharov's rule only says the preference must exist. It never promised the preference would be large enough. And when the accountants of physics run the numbers, the preference we can measure falls short of the observed universe by a factor so vast that it stops being a rounding problem and becomes a hole in the theory. Something is missing. That is the honor shape of it. The standard model, the finest description of particles ever written, the one that has predicted so much with such staggering precision, cannot on its own explain why you are here to consider it. Its cheating is genuine, and its cheating is too weak. So the true source of your existence has to be something the model does not yet contain. An unknown particle, an unknown force, some new layer of physics that no collider and no detector has yet pulled into the light. That is where the field splits, and the argument gets interesting. One camp looks away from the heavy quarks entirely and turns to the ghost of the particle world, the neutrino. Neutrinos barely touch ordinary matter. Trillions pass through you every second and leave no mark at all. But if neutrinos and their antimatter twins behave even slightly differently from one another, that difference could have seeded the imbalance in the newborn universe and then passed it down to everything that followed. This idea carries a name, leptogenesis. It moves the whole mystery out of the quarks that build your body and hands it to the faintest particles known, the ones that hardly notice you exist. A second camp keeps its attention on weight. Perhaps the answer is not a ghost but a giant. Some particle so heavy that no machine ever built has carried the energy to make even one. If such a thing existed in the first instant and then decayed, tipping ever so slightly toward matter as it fell apart, it could have left behind the exact residue we measure. The difficulty is plain and painful. If it is too massive for our accelerators, we cannot create it, and we cannot watch it break. Its fingerprints would sit in the early universe alone, long gone. And a third camp holds the hardest possibility of all, that the answer sits somewhere no experiment we can imagine building will ever reach, at energies far beyond any machine, in a corner of nature we have not yet learned how to even question, not hidden by accident but hidden by scale, beyond the practical limit of every accelerator the human species knows how to construct. It is worth being plain about what this is. This is not a settled question dressed up as a mystery for the sake of a little wonder before sleep. It is a real, open wound in physics. Frank Wilczek, who shared the Nobel Prize for his work on the force that binds quarks, has placed the matter and antimatter imbalance right beside dark matter and dark energy, among the deepest unsolved problems that tie the smallest particles to the shape of the whole cosmos. No one has closed it. There is no quiet consensus waiting behind the scenes. The best-funded experiments on the planet are still arguing about where to even point. And notice what the argument is truly about. It is not a technicality. It is not a missing decimal. It is the question of why there is a universe with things inside it, rather than a universe of pure light and nothing else. Every camp, the neutrino people, the heavy particle people, the ones reaching past every machine we own, is chasing the same single prize. They are trying to name the reason anything survived the first second at all, the reason the great annihilation left a remainder instead of a clean, silent, perfect zero. 60 years have passed since Cronin and Fitch first caught the mirror cracking in a kaon. In that time, the measurements have grown exquisite. The machines have grown enormous. The confidence levels have sharpened to 5 sigma and beyond, past the line where doubt is supposed to end. And still the central number will not balance. Everything found so far is genuine. Everything found so far is too weak. The cheating was real, but it was far too small, and so the search moved to stranger suspects. The cheating was real, but it was far too small, and so the search moved to stranger suspects. The strangest suspect of all is a particle you have never once felt. It is called the neutrino. trillions of them are streaming through your body as you lie here, through the mattress, through the floor, through the whole planet beneath you, and not one of them touches a single atom you're made of. They come from the sun, from exploding stars, from the reactor cores of distant galaxies. They carry almost no mass. They carry no electric charge. And for decades, physicists have wondered whether this ghost might be hiding the answer to why you exist. Here is the idea, held gently. The imbalance that saved matter did not have to begin with the protons and neutrons in your bones. It could have begun with the neutrinos, and then spread. If neutrinos and their mirror twins, the antineutrinos, behave even slightly differently from each other, that difference is a form of the same broken symmetry, the same faint preference for matter over antimatter, only in a different family of particles. Physicists call that family the leptons, and they have a name for the early process that might have carried the imbalance outward into everything else. They call it leptogenesis. Think of it as a seed. In the first flickering instant of the universe, heavy neutrinos decay. If they decay just a little more often into matter than into antimatter, they tip the scales. That tiny lean, born in the ghost particles, gets handed down, converted through the physics of that hot young cosmos into the surplus of ordinary matter we see today. It is elegant, because it explains two mysteries with one stroke. It explains why neutrinos have their strange tiny masses, and it might explain why the antimatter did not win. But it only works if neutrinos and antineutrinos truly differ. And so, to test it, physicists built something almost absurd. They decided to make a beam of neutrinos, aim it through the solid body of the Earth, and see whether the matter beam and the antimatter beam arrive changed by different amounts. Two machines are doing this right now. One is in Japan, an experiment called T2K. The other is in the United States, an experiment called NOVA. Each one fires a beam of neutrinos, then a beam of antineutrinos, hundreds of miles through the rock of the planet to a detector waiting at the far end. Along the way, the neutrinos quietly change identity. They oscillate, shifting from one type into another as they travel, and the question is whether the matter version shifts by a different amount than the antimatter version. If it does, you're watching the broken symmetry in the act. For years, the hints were tantalizing and blurry. The two experiments each saw a lean, a suggestion that neutrinos and antineutrinos were not perfect mirrors, but neither could nail it down alone. So in October of 2025, they did something they had never done before. They combined their data into a single joint result and published it together in the journal Nature. Between them, they narrowed the allowed difference in neutrino and antineutrino behavior to within about 2%. It was the most precise measurement of its kind ever made. Not a discovery, not yet, but a vice, closing slowly around the answer. And now, under a mountain in South Dakota, physicists are building the machine meant to finish the job. The place is a town called Lead, high in the Black Hills. For more than a century, men went down into the rock there to dig for gold. The Homestake mine was one of the deepest and richest in the country. When the gold finally ran out, the tunnels did not close. They became a laboratory. Today it is called the Sanford Underground Research Facility, and nearly a mile below the surface, in the cold and the dark and the silence, physicists have carved out something enormous. In 2024, the crews finished excavating the caverns. They hollowed out chambers big enough to swallow buildings, blasting and hauling out hundreds of thousands of tons of stone. Into those caverns will go the heart of the experiment. The name of the whole thing is Dune, the Deep Underground Neutrino Experiment, and the plan behind it is the boldest version yet of that same strange idea. Fire a beam through the Earth, and watch antimatter and matter refuse to match. The beam will be born nearly 800 miles away, at Fermilab, outside Chicago, in Illinois. There, protons will be slammed into a target to spray out neutrinos, and those neutrinos will be pointed straight down into the ground, aimed at South Dakota. There is no tunnel for them. They do not need one. The beam simply goes through the planet. through 800 miles of solid continental rock, and comes out the other side to arrive in the waiting detectors beneath the old gold mine. And what waits for them there is worth picturing slowly. The detectors are vast tanks, filled with liquid argon. Argon is a gas in the air around you right now, but chilled far enough, it turns to a clear, dense liquid. To keep it liquid, Dune holds it at about 302 degrees below zero Fahrenheit. Let that number settle. That is colder than the surface of Pluto. Down in the dark, under a mile of rock, in tanks colder than the most distant world in our solar system, physicists are waiting for a ghost to leave a fingerprint. Because that is what a neutrino detector really is. It is a trap for something that almost never gets caught. Picture the beam again. 800 miles of stone, and the neutrinos pass through it the way sunlight passes through a pane of clear glass. The glass is solid. Your hand cannot go through it, but the light does, as though the glass were not even there. That is what the whole Earth is to a neutrino, not a wall, a window. The rock, the iron core, the oceans overhead, all of it is transparent to this particle, and yet not quite perfectly transparent. One time in billions, a single neutrino, out of the unimaginable flood pouring through the argon, will strike a nucleus and leave a tiny spark of light and charge in the cold liquid. That one interaction, that one flash in the dark is what the miracle depends on. The detectors are built so large, and the beam is aimed so precisely that even at odds of 1 in billions, a handful will be caught. Count enough of them from the matter beam, count enough from the antimatter beam, and if the two counts disagree, you may be looking, at last, at the reason there is a universe here to look at all. It will take years. The machine is not finished, and even when it speaks, it may not settle everything, because a hard question hangs over the whole hunt. Nobody yet knows whether neutrino asymmetry, even if Dune finds it clearly, would be big enough. Leptogenesis is a beautiful idea, but it is still only an idea. The difference the machines are chasing might turn out to be real, and still too small, another partial clue rather than the whole answer. That honesty matters. The neutrino is the leading suspect. It is not a convicted one. And that is why some physicists have started to wonder whether the answer is not a missing particle at all, but a missing half of everything. Consider a thought that sounds like a dream, but is written in real equations by serious people. Two physicists, Neil Turok and Latham Boyle, working at the Perimeter Institute in Canada, asked a simple question in a radical way. What if the antimatter did not vanish? What if it is simply somewhere you cannot go? Their proposal reimagines the Big Bang itself. In the ordinary story, the Big Bang is a beginning, a wall of time with nothing before it. In their story, the Big Bang is not a wall, it is a mirror, and on the far side of that mirror, reflected through the very first instant, there is another universe. That universe is not empty. It is made overwhelmingly of the antimatter that our side is missing. And stranger still, on that side, time runs the other way. From the mirror point, that antimatter cosmos expands backward, away from ours, into its own deep past that is, in a sense, our shared origin. The reason they suggest it is not to be poetic, it is to obey a law. Physicists cherish a deep symmetry called CPT, which combines three reversals at once: charge, flipped; parity, the mirror flip of space; and time, run in reverse. The Standard Model insists this triple symmetry must hold, always, everywhere, and a single lopsided universe, all matter and almost no antimatter, seems to break it. But a matched pair, one universe of matter running forward and a twin of antimatter running backward, restores the balance perfectly. The two together are the mirror image the law demands. You do not need to explain where the antimatter went. It never went anywhere. It is simply on the other face of the beginning, and you are looking at its reflection every time you look at yourself. Hold this idea loosely, the way you would hold a stone you're not sure you want to keep. It is a minority view. It is actively argued over, poked at, resisted by many, and it is not the standard picture that most cosmologists teach. It may well be wrong. It solves the puzzle by refusing the premise, by saying the antimatter was never lost, only hidden by the geometry of time. That is either profound or a sleight of hand, and the physics community has not agreed which. Even so, that a real theory can even be written, a universe running backward, made of the stuff you are not, sharing your birth instant like a twin you will never meet, tells you how open this question still is. So the search has spread wide. Down in the Argonne, physicists chase the ghost that barely touches anything, betting that its faint preference for matter will explain the rest. In the equations, others sketch a mirror world on the other side of the first moment and ask whether the missing antimatter was ever missing at all. Neither answer is finished. The neutrino may lean the right way and still lean too little. The mirror universe may be beautiful and still be untrue. What they share is a single stubborn fact. The imbalance is here, written into every atom you are, and the deepest machines and the boldest theories have not yet closed the case. There is something almost gentle in that. The people who built a detector colder than Pluto, nearly a mile under an old gold mine, aimed a beam through 800 miles of rock, and imagined a twin cosmos flowing backward through the Big Bang. All of them are still at this hour uncertain. They are patient in the way the universe is patient. They wait for one neutrino in billions to flash in the cold. They wait for the data to speak. They do not pretend to know more than they know. And while they wait, you do not have to travel to South Dakota or to Japan or to the far side of time to find antimatter. That is the quiet turn in this whole story. The exotic thing the machines are straining to catch is not only far away and long ago. There are machines built for nothing else. Not to imagine antimatter, not to model it, but to hold it in place long enough to read its properties off a screen. The most patient of them sits at CERN, in a low building with a plain name, the Antimatter Factory. Inside it lives an experiment called Alpha, and its whole purpose is to make the antimatter version of the simplest atom there is. Ordinary hydrogen is one proton with one electron circling it. Antihydrogen is the mirror image, one antiproton with one positron, a tiny knot of the very stuff that should have cancelled you out. Making it is the easy part. Keeping it is the trouble. Antihydrogen has no electric charge, so you cannot steer it with the fields that hold ordinary particles. Touch a wall, touch a stray speck of gas, touch anything made of matter at all, and it annihilates in a flash and is gone. So Alpha builds a bottle out of magnetism, a trap with no solid sides, and it chills its ingredients to within a whisper of absolute zero so they move slowly enough to be caught. Across its experimental runs in 2023 and 2024, Alpha produced more than 2 million atoms of antihydrogen. 2 million complete antimatter atoms, assembled one at a time from the rarest material human beings know how to make. And with those atoms, the experiment answered a question that had been open for decades. People had wondered quietly and seriously whether antimatter might fall up, whether gravity, which pulls every ordinary thing down, might push antimatter the other way. If that were true, it could explain where all the missing antimatter went. It could have drifted off, away from the matter, and hidden somewhere out in the dark. So Alpha built a tool version of its trap, released the antihydrogen, and simply watched which way it went. In 2023 it saw the answer, and in 2024 it confirmed it. Antihydrogen falls down. It drops toward the floor at the same steady pull as a raindrop or a stone. There is no anti-gravity. The mirror stuff obeys the same law you do, which means it did not simply float away. The mystery stays exactly where it was, and that is somehow more unsettling than an easy escape. Take a moment here, if you are still awake enough to. A like or a quiet subscribe helps this channel more than you would guess, and every episode is on Spotify too if you drift better with just the voice. That is the whole ask. Now let the trap fall back out of view, because Alpha works on the ground, and the search does not stop at the ground. 250 miles above your head, bolted to the outside of the International Space Station, there is a second machine, and it has been up there since 2011. It is called the Alpha Magnetic Spectrometer, AMS-02 for short, and it cost roughly $2 billion to build and to launch. It clings to the truss of the station like a barnacle fixed to the hull of a ship, riding through orbit at about 17,000 miles an hour, facing out into the rain of cosmic rays that the atmosphere below would otherwise soak up before any of it reached the surface. Its job is to sort that rain. Cosmic rays are mostly ordinary matter, protons, and the nuclei of light elements flung across space by dying stars. AMS-02 counts them, one by one, sifting billions of particles as they pass through its magnet, bending each one by its charge, weighing it, reading it. And what it is truly listening for is a whisper underneath the roar. It is looking for heavier antimatter, in particular antihelium, an entire antimatter nucleus of 2 antiprotons and 2 antineutrons bound together. That is far harder to make by accident than a lone antiproton. If antihelium is drifting through space in any real quantity, it hints at something big out there, whole regions of antimatter, or some source no one has named. AMS-02 hunts for it at a sensitivity of about 1 part in a billion, meaning it can flag a single antihelium nucleus hidden among billion ordinary ones. And here is the strange part, the part the physicists themselves are careful with. Over its years in orbit, AMS-02 has recorded a small handful of candidate events that look like antihelium. Not many. Something on the order of 1 a year. Each one is a track through the detector that fits the profile of a heavy antimatter nucleus, and each one is flagged, openly and explicitly, as unconfirmed. It might be real. It might also be background, a fluke of the instrument, an ordinary particle wearing a convincing disguise. No one has ruled that out. So the count sits there, a few unexplained marks in a ledger of billions, too few to celebrate and too stubborn to dismiss. That is what an honest search looks like at the edge of what a machine can measure. You do not need to leave the neighbourhood of Earth to find the mirror stuff, though. Some of it is trapped right here, wrapped around the planet you are lying on. High above the atmosphere sit the Van Allen belts, great rings of charged particles held in place by Earth's magnetic field, the same field that swings a compass needle. Cosmic rays slam into the top of the atmosphere, and in those collisions a few antiprotons are born. Most escape. But a thin population of them gets caught in the magnetic field lines and held, circling the planet in a faint girdle of antimatter that no eye could ever see. An Italian and Russian satellite called Pamela went looking for that girdle. Over roughly 2.5 years of patient observation, it detected 28 of these trapped antiprotons. 28. It is a small number to describe something that circles the entire world, and yet inside the belt the concentration is remarkable. Where those field lines gather the antiprotons, they sit about 1,000 times more densely than the free antiprotons drifting loose in ordinary cosmic rays. 1,000-fold enrichment, a genuine reservoir of antimatter held in orbit by the planet itself. And still, weigh the whole thing, and it comes to almost nothing. Add up every trapped antiproton in that entire belt wrapped around the Earth, and the total mass is likely under a single microgram. Less than the weight of a grain of pollen, spread out in a ribbon thousands of miles across. That is the paradox of this material in miniature. It is 1,000 times concentrated, and it is barely there at all, both at once, because there is so staggeringly little of it in the universe to concentrate. Notice what all 3 of these machines share. None of them is speculating. Alpha is not arguing about antimatter. It is holding 2 million atoms of it and dropping them to see which way they fall. AMS-02 is not theorizing about antihelium. It is riding the outside of a space station counting particles at 1 in a billion, and marking down the ones it cannot explain. Pamela did not predict trapped antiprotons. It flew through the belt and returned with 28 of them logged and weighed. These are hard numbers, gathered by real instruments, right now, in this decade. The mirror stuff that the Big Bang almost used to erase you is not a story someone tells. It is a measurement, taken in a magnetic bottle, taken in orbit, taken in a belt around your own planet, and every reading agrees that it is genuinely here, faint and rare and utterly real. While those machines hunt for the answer underground, antimatter is already all around you and inside you tonight. While those machines hunt for the answer underground, antimatter is already all around you and inside you tonight. It is not locked away in a laboratory. It is not a prop from a science fiction film. It is being made right now in the quiet dark of your own chest, and it has been made there every night you have ever slept. Somewhere inside you, in this last minute alone, a few particles of antimatter have flickered into being and vanished again, each one erasing a sliver of you into light. Here is how. Your body carries a faint permanent radioactivity, and you cannot switch it off. It comes mostly from an isotope called potassium-40, folded into the potassium in your muscles and your blood and your bones. Inside an average adult, potassium-40 breaks apart at a rate of roughly 4,000 to 5,000 disintegrations every second. That is happening as you lie here. 4,000 to 5,000 tiny nuclear events every second for the whole length of your life. If you are still awake enough to enjoy one small thing before you drift, this is it. Consider giving the video a like or a subscribe if the channel helps you sleep and know it lives on Spotify too. That is the whole ask. Now let the numbers carry you. Most of those potassium decays send out an ordinary electron, but a small fraction do something stranger. A small fraction emit a positron, and a positron is antimatter. It is the mirror twin of the electron, identical in almost every way, except that its charge is flipped from negative to positive. The instant that positron appears inside you, it is already doomed. It travels only the smallest distance, a fraction of the width of a single cell, before it meets one of your own electrons, and when a particle of matter meets its antimatter twin, they do not bounce apart. They annihilate. They cancel each other completely, and both of them turn into pure light. So think about what that means as you settle deeper into the mattress. A fragment of your own body, an electron that belonged to you, meets a scrap of antimatter your body just manufactured, and the two of them convert into a soft pulse of gamma radiation. You never feel it. It is far too small and far too fast, but it is real, and it is constant. A part of you is quietly turning into light, over and over, thousands of times as you fall asleep, and it has been doing this without pause since before you were born. You can picture it as a spark struck somewhere behind your ribs. Not a spark of fire, not warmth you could ever notice, just a single flash too faint to register, gone before the thought of it can form, strike and gone, strike and gone. A body full of these little sparks blinking on and off in the dark, every one of them a complete and perfect erasure of matter into energy. If that feels too abstract to hold, put a banana in your hand instead. A banana is famously rich in potassium, and so it carries the same potassium-40 you do. Because of that isotope, a single ordinary banana emits roughly one positron every 75 minutes. One little pulse of antimatter from a piece of fruit sitting in a bowl on your counter. Think of it as a slow clock. Every 75 minutes or so the banana ticks, and the tick is a particle of antimatter blinking into the world and instantly cancelling itself against the fruit around it. Nothing about the banana looks unusual. It ripens, it browns, it waits. And all the while it is keeping this strange silent time, one antimatter tick after another, patient as a metronome no one can hear. Now lift your gaze from the fruit bowl to the sky, because the storms above you do the same thing on a far grander scale. For years this was only suspected. Then, in 2011, NASA confirmed it. The Fermi Gamma Ray Space Telescope in orbit around the Earth caught ordinary thunderstorms flinging beams of antimatter up into space. The mechanism sounds almost impossible, and yet it is simple. Near the top of a powerful storm, the electric fields grow so intense that they accelerate electrons to nearly the speed of light. Those racing electrons throw off gamma rays, and some of those gamma rays convert into pairs of particles, an electron and its antimatter twin, the positron, born together out of raw energy. One night gave the clearest proof of all. On the 14th of December, in 2009, the Fermi telescope was flying high above Egypt when it registered something curious. A burst of positrons was annihilating directly against the spacecraft itself. The antimatter had not been made in orbit. It had been hurled upward from a storm churning far below, thrown clear of the atmosphere and into the path of the satellite. A thunderstorm on the surface of your planet had briefly become a fountain of antimatter, and a telescope happened to be flying through the spray. And this is not rare. These events are called terrestrial gamma ray flashes, and the best estimates say about 500 of them happen somewhere in the world every single day. Most are never seen. They last less than 1,000th of a second, invisible to any human eye buried inside the noise of a storm. But in that sliver of an instant, an ordinary thunderhead becomes one of the most powerful natural particle accelerators anywhere on Earth, briefly outdoing anything a human being has ever built, and it does it without anyone below ever knowing. Somewhere, on almost any given night, while you're sleeping, a storm is throwing antimatter at the stars. It helps to sit for a moment with what annihilation actually is, because it is the most complete transformation in all of physics. When matter and antimatter meet, they do not simply release some of their energy the way a fire does, or the way even a nuclear bomb does. They release all of it. 100% of their mass becomes energy, following Einstein's most famous line that energy equals mass times the speed of light squared. Nothing is left behind, nothing is wasted. Every last scrap of the matter and the antimatter becomes radiation. To feel how extreme that is, compare it to the reactions you already know. Burning fuel, the chemistry of a flame, is a rearranging of atoms, and it liberates only a whisper of the energy locked inside them. Annihilation is roughly 10 billion times more energetic, gram for gram, than a chemical reaction like that. It leaves even nuclear power far behind. A nuclear weapon converts well under 1% of its material into energy. Annihilation converts all of it. It is as efficient as the universe allows anything to be. Run the number, and it will keep you awake for a breath. A single ounce of antimatter, about 28 grams, roughly the mass of a small handful of coins, would release something on the order of a 1.2 megaton blast if it fully annihilated. That is in the range of a large modern thermonuclear weapon, out of a lump of stuff smaller than a shot glass of water. And yet you can lie here calmly, because the strange truth is that this could never be built. The energy would come out mostly as an invisible flood of gamma radiation and ghostly neutrinos, more a searing burst of light than a wall of blast. And far more decisively, there simply is not enough antimatter and never will be. That is because antimatter is the most expensive substance human beings have ever priced. Estimates place it in the range of tens of trillions of dollars for a single gram, a figure so large it stops meaning anything. There is a reason for the price. It is almost impossibly hard to make. The great antimatter factory at CERN, the most capable in the world, produces only a few billionths of a gram in a year. At that rate, to gather one full gram, one paperclip's worth of the stuff, would take something like 1 billion years. The universe is not quite 14 billion years old. You would need a meaningful fraction of the age of everything just to collect a single gram, one careful atom at a time. So the antimatter that surrounds you is real, and it is genuinely everywhere. And yet it exists only in the tiniest imaginable amounts. A few positrons from your own tissue, one tick from a banana every hour and a quarter, a flash from a distant storm, and the same physics you carry in your body is also, gently, healing people in hospitals every day. A PET scan, the kind of scan that hunts for cancer and studies the living brain, works by placing a small dose of a positron emitter inside the patient. Each positron annihilates against an electron within a fraction of an inch, and the paired flashes of light it makes are caught by a ring of detectors and turned into a map of the body from the inside. The very process that once nearly erased all matter from existence is now, in a controlled and gentle form, used to find a tumour before it can grow. Hold all of it together for a moment, here in the quiet. The isotope ticking in your bones, the banana keeping its slow secret time on the counter, the storms flinging light-speed particles above the clouds, the scanner in a hospital reading the annihilation glow to save a life. It is all the same physics, the same meeting of matter and its mirror, the same instant conversion into light. It has been there the whole time, woven through the ordinary world, hiding in fruit and weather and your own sleeping chest. And that is the thought to carry down into sleep tonight. You are not merely made of matter. You are, in the smallest and truest sense, a maker of antimatter and an unmaker of it, all at once, all the time. Right now, as your breathing slows and your thoughts begin to loosen, particles of antimatter are being born inside you and dying inside you, each one a perfect little erasure, a fragment of you turning into light and slipping away. It happened last night. It happened the night before. It has happened every single night of your entire life, and you never once had to think about it. There is a strange comfort in that. The thing that should have destroyed the whole universe, the substance that cancelled almost everything in the first instant of time, is the same substance your body handles casually, thousands of times a second, without harm, without effort, without your knowledge. You have been living peacefully alongside the most explosive material in physics your entire life, and it is a part of you. So you can rest inside genuine wonder. The antimatter is not a threat and never was, not in these amounts. It is a quiet companion, flickering in your tissue, ticking in your food, arcing above the storms, glowing in the machines that keep people well. It is proof that the deepest and most violent physics in the cosmos did not stay locked away at the beginning of time. It came down into the ordinary world, into bananas and thunderclouds and the beating warmth of your own body, and it settled in to stay. There is a machine in almost every large hospital that runs on antimatter. You have probably walked past one without knowing what it was. It is called a PET scanner, short for positron emission tomography, and it works by making a small amount of antimatter appear inside a living person, on purpose, and then watching it disappear. It begins with an injection. The patient receives a tracer, a molecule built to look almost exactly like ordinary blood sugar. Your cells cannot easily tell the difference. They pull it in the way they pull in glucose greedily, because sugar is fuel. The trick is what is hidden inside that sugar. One atom in the molecule has been swapped for an unstable isotope, a version of an element that emits positrons. A positron is an antimatter electron. It is the same particle Carl Anderson first saw curving the wrong way in 1932, now dripped quietly into a vein. Then you wait. The tracer travels with your blood, spreads through your body, and settles where your cells are working hardest. Tissue that burns the most sugar takes up the most tracer. A tumour is often exactly that kind of tissue. Cancer cells divide fast and feed fast, so they hoard the labelled sugar and glow brighter than the tissue around them. The same is true of a seizure focus in the brain, or a patch of tissue starved of blood. The tracer sorts your body by appetite. While it sits there, the unstable atoms are decaying. Each decay flings out a single positron. That antimatter particle does not travel far. It moves only a fraction of an inch through your tissue, losing speed as it goes, bumping through a crowd of ordinary electrons. Your body is full of electrons. It does not take long. Within a fraction of an inch of where it was born, the positron meets one of your own electrons, and the two touch. They cannot coexist. Matter and antimatter of the same kind cancel. In that instant, the positron and the electron annihilate, and both of them stop being particles at all. Their entire mass is converted into light. 2 flashes of gamma radiation, exactly as Einstein's equation says it must. Each flash carries 511,000 electron volts of energy, the precise fingerprint of an electron and a positron dying together. The two of them add up to 1.022 million electron volts, the mass of both particles turned back into pure energy. Here is the detail the whole machine depends on. The two gamma rays do not fly off in random directions. They leave back to back, in a nearly straight line, one racing one way and the other racing the opposite way, like the two halves of a snapped twig springing apart. Momentum forces it. The positron and electron had almost none between them, so the light they become must balance out, one flash for the other, aimed in opposite directions. Every annihilation inside you sends out a matched pair along a single line through your body. That is what the scanner listens for. The patient lies inside a ring, a smooth circle of thousands of small crystal detectors packed shoulder to shoulder all the way around. Each crystal waits for a gamma ray to strike it and flash. On its own, a single flash tells you almost nothing. You would not know where it came from. But the machine is not watching single flashes. It is watching for two of them, arriving at the same instant, on opposite sides of the ring. When two detectors light up together, within a few billionths of a second of each other, the scanner treats them as partners. It decides those two gamma rays came from the same annihilation, and because it knows they left back to back along one straight line, it can draw that line. The annihilation happened somewhere along the path connecting the two detectors that fired. One event gives you one line through the body. It does not yet tell you where on the line, so the machine gathers millions of them. Every second, deep in the loaded tissue, positrons are being born and dying, thousands upon thousands of annihilations, each one throwing its paired gamma rays out to the ring. The scanner records line after line after line, each a straight thread stitched across your body. Where the tracer is thin, few lines cross. Where the tracer is concentrated in that hungry tumour, in that seizing patch of brain, the lines pile up and overlap, crossing again and again through the same small volume of space. A computer takes all those crossing lines and works backward. Where many lines intersect, there must be a bright source of annihilation, which means a heavy load of tracer, which means cells that were burning sugar fast. Point by point, the machine rebuilds a three-dimensional map of that appetite. There is a natural softness to the picture, because each positron drifts that fraction of an inch before it dies, so the glow is always marked a hair away from the atom that made it. Even so, the map is clear enough to save lives. It is not a photograph of your anatomy. It is a map of where your body was spending energy, drawn entirely from the light of vanishing antimatter. That map is read by doctors every day. A PET scan can find a tumour that no other image has caught yet because it sees the cancer's hunger before it sees its shape. It can locate the exact spot in the brain where an epileptic seizure begins, so a surgeon knows where to go. It can show the dimming pattern of glucose use across a brain in the early years of Alzheimer's, a fading of activity in regions that should be bright. Whole branches of medicine, in cancer, in neurology, in the heart, now lean on this one quiet trick. Sit with what is actually happening in that room. A person lies still on a padded table. Inside them, in a tumour no one can feel, a positron of antimatter meets an electron of matter, and the two erase each other in a spark of gamma light. That is the same reaction, particle for particle, that once nearly emptied the early universe. The same meeting of matter and its mirror, the same conversion of mass straight into radiation. It happened countless times over across all of space in the first second of everything, and it is happening now, gently, one particle at a time, a few inches under a patient's skin. The difference is only one of scale and control. In the newborn universe, the annihilation was almost total, a near-complete self-erasure that left barely a survivor in a billion. In the scanner it is a whisper, a trace of unstable atoms, chosen and timed, releasing their antimatter a few positrons at a time, each one lasting less than a blink before it meets its end. The machine does not fear that fire, it aims it. It uses the faint, controlled echo of the largest catastrophe in history to go looking for something as small and human as a shadow on a lung. And this is not exotic. Your own body already runs a smaller version of it without any machine at all. The potassium in your muscles and blood includes a trace of an unstable isotope, potassium-40, and it decays thousands of times every second inside you. A fraction of those decays throw off a positron, exactly as the tracer does, and that positron annihilates against one of your electrons and turns a sliver of you into light. You've been making and destroying antimatter faintly every second of your life. The PET scanner only borrows that same process, brightens it, and points it where a doctor needs to look. So when we say antimatter is real, this is what we mean, in the plainest possible terms. Not a starship fuel out of a story, not a threat locked in a vault, a tracer in a vein, a positron travelling a fraction of an inch, 2 gamma rays leaving back to back at 5 or 11,000 electron volts each, a ring of crystals catching them in pairs, and a map of a living body drawn from the light of matter meeting its opposite. We can make it. We can measure it. We can build it into a tool and hand it to a surgeon. And yet, for all the antimatter we can make and measure, the one question that matters most is still unanswered. And yet, for all the antimatter we can make and measure, the one question that matters most is still unanswered. Why is there anything here at all? Why did the universe keep a little, when the simplest arithmetic says it should have kept nothing? Picture the ledger of everything, one last time. On one side, a near-infinite mountain of matter. On the other side, a near-infinite mountain of antimatter, almost perfectly equal. Almost. The 2 columns rise together, then collapse into each other, cancelling pair by pair until the page is nearly blank, and at the very bottom, below that colossal cancellation, there is one thin line left standing, 1 part in a billion, a residue so faint it is almost a rounding error. That thin line is everything. It is the iron in your blood and the calcium in your teeth. It is the water in this room, the air moving in and out of you, the warmth of the blanket over you tonight. Every star you have ever seen was built from that leftover layer. Every person you have ever loved is made of the fraction the universe forgot to destroy. You are not what the cosmos was made of. You are what it failed to erase, and the erasing left a light behind. At the centre of our galaxy, tens of thousands of light years from here, there is a steady glow that no telescope you own could ever see. It shines at a single precise energy, 511,000 electron volts, the exact fingerprint of an electron meeting a positron and vanishing into gamma rays. It is the light of antimatter dying, and it has been pouring out of the galactic centre since the 1970s, seen by one gamma-ray telescope after another for more than 50 years. No one knows what is making it. Something out there is producing positrons in enormous numbers, near the heart of the Milky Way, steadily, patiently, for longer than these instruments have existed. It might be the corpses of dead stars. It might be radioactive ash from ancient supernovae. It might be dark matter quietly annihilating in the dark. Every explanation fits a little, and none of them fits all of it. It is a candle no one lit, burning at the centre of our own galaxy, and after half a century we still cannot name the flame. This is the shape of the honest answer. The physicist Frank Wilczek, who has spent a lifetime inside these equations, places the missing antimatter where it truly belongs. It stands beside dark matter and dark energy, 3 great blank spaces in our map of reality. 3 places where the best physics on Earth points at something and admits it cannot yet say what. We can build the machines, we can trap the antihydrogen, we can watch a baryon and its mirror twin decay at slightly different rates. And still, when you ask why you're here to watch any of it, the true reply from the finest laboratories ever built is quiet and unembarrassed. We do not fully know. Let that sit gently for a moment. Not as a failure, as an opening. There is something steadying about a question this old and this unfinished. 60 years of the sharpest minds, the coldest tanks, the largest detectors, and the mystery is still there, still waiting, still yours to wonder about. You do not have to solve it tonight. You do not even have to hold on to it. You can simply let it be true, the way the stars are true whether or not anyone is watching. Feel how strange your own existence is, one more time softly. In the first second of everything, nearly all of it cancelled. 1,000,000,001 against 1,000,000,000, and the 1,000,000,000 lost. You are the one that remained. You are the survivor of the largest disappearance that has ever happened. A thin, improbable line at the bottom of the ledger, warm and breathing and here. Nothing about you was guaranteed. The arithmetic did not owe you a single atom, and yet here you are, resting in the quiet, made entirely of the part that lasted. Somewhere right now a positron is forming inside you and vanishing again, a tiny echo of that first cancellation, harmless and constant. Above some distant thunderstorm, antimatter is streaming into space. In a hospital across the world, a scanner is reading the light of annihilation to find and heal what is hidden. And at the centre of the galaxy, that unexplained glow keeps shining, keeping it secret, waiting for someone not yet born to understand it. You do not need to be that person. Tonight you only need to rest, knowing the question is safe, that it will still be here in the morning, patient as ever. You are the rounding error that survived. The leftover the universe could not quite cancel, and that is enough. That is more than enough. Let the mystery keep its watch over the galaxy while you let go of the day. Breathe out slowly. The universe did the improbable thing once, and the result is you, lying here, held together by the one part in 1,000,000,000 that stayed. Rest now inside that unlikely ordinary miracle. Sleep well tonight. Good night.